Okay, so welcome to the third class of Introduction to Quantum Computing, where I try to introduce the best I can the intuition behind this emerging technology set. I think I may have given you a brief background a little bit, that my original inspiration for this class was the realization that at some point, quantum computing, at least the branch of quantum computing that is the seminal branch, the sort of like the original frontier, comes down to a bunch of mathematics that should be familiar to even high school students, and that is matrix algebra. Right. That's my inspiration for why I think I could even make this a Gen Ed class, is to say, well, Chulalongkorn students come in and they may not every department, every faculties place a lot of emphasis on mathematics, but at least you guys came from high school. You must have done some linear algebra, and if not, I can, bring you up to speed. Okay, and that last week was, in a way, a little bit of that. But I couldn't help but giving you insights along the way of how quantum computing sits in relation to quantum mechanics as a whole. Okay, so I like to say that physics, right? Physics has taken a long journey. You can say that this journey started pretty much with classical mechanics of Newton, like 300, 400 years ago, and culminated in early 20th century, 1920s, 1930s, quantum mechanics. Okay? And in fact, the insight that I will touch on about quantum mechanics will stop there. There's a lot more work, after the war, like quantum field theory, that we don't need to go through. The point is that some of the insight that I would like to add, again, this being a Gen Ed, right? So nothing is beyond purview of education. It's about showing you a little bit how quantum mechanics came about. And the upshot of it is, I will show you that, quantum mechanics involves a lot of math, but quantum computing is essentially a lot of simplification. So as I will be giving that talk probably next class, right? Where I start to trace from quantum mechanics all the way to quantum computing. Okay. Hopefully, the feeling you would come away with next class is that, oh God, thank God you're just learning quantum computing, because it's much easier, it's much simpler. Okay, and therefore, there's no introduction to quantum computing Gen Ed course, but there's an introduction to there's no introduction to quantum mechanics Gen Ed course, but we can reasonably have introduction to quantum computing Gen Ed course, right? So that's my thesis. So anyway, the field of physics is very heavily mathematicalized. I like this picture. Nowadays I use large language model quite a bit to summarize or generate infographics of things I want to say. And this is kind of picture I would like you to get in the back of your mind. It's like physicists, okay? Physicists. You can think of physicists as three stages, okay? The first generation of physics, right? Think of Newton, okay? Okay, think of Newton. Newton observed that apple falls, right? Planet move, right? So he tried to deduce from that the law of motion. So doing physics was about discovering law, right? The famous law is F is equal to ma. Okay, you apply force in one direction, and something that has a mass gets accelerated in that direction. right? And that mass is kind of like a resistant inertia. So if you have a lot of mass to get to the same acceleration, you have to apply a lot of force, right? So this would be a bit like you walk to a park, you watch people playing chess, and you try to deduce, because you don't know chess before, how does it work? And then you come with the conclusion that, oh, okay, this little guy moved forward, this little guy looks like a horse, moved this way. Okay, so that become kind of like codified observation of nature. Okay, so you can think of physicists in a way, a scientist. It's just observing nature, recognizing there's a regular pattern to it. So it's not random. So there's a pattern to it. So the pattern is the pattern that Newton would have observed is that, well, you never apply force in this direction and the acceleration go the other way, right? So that the acceleration is always in line with the direction of the force, right? And if you have two things, one is twice as massive, applying the same force, then the acceleration is half as much, something like that. So he induced the mathematical relationship from that. So think of mathematics from that point on as nothing more than a codification of a regular, predictable observation. So that the next time he comes in, he see the force and see the same mass, we get the same acceleration. And he asked himself, what if the mass were to triple? Well, what would happen? Well, the acceleration would go down by a factor of a third, right? So that's kind of like discovering law, okay? Law of nature. So that's the first generation of physics, so to speak. Well, the second generation of physics came very, by the way, this is not a standard terminology of first generation, second generation, but this is how I think. The next group of people are, you probably never heard of him, Hamilton and Lagrange. What they did was they actually reformulated what Newton did. F is equal to ma, right? But they did it in a very clever way. They did it by discovering not law of motion, but discovering the principle by which nature operates. And that principle they discovered was called stationary action. Never mind. The point is that instead of trying to make an equation that describes things happening, he kind of induced that nature operates in this principle. Yeah. I'll give you a good example. Have you guys, actually, I have a picture of that. I have a picture of that. It's called, that's a picture of me swimming. Never mind. Okay, this is a nice story. So again, today we'll do Mathematica, but let me give you some insight just to ease you in. Okay, so, a couple of years ago, not many years ago, I was big into triathlon and all that stuff, right? And one of the things I really liked was open water swimming. Okay, meaning, I don't know if you guys know what Got Summit is. And this is Banpei. Okay, and this is about, let's say, 2+ kilometers. Okay, now I ended up swimming like 4 kilometers because I was not swimming in a straight line. Okay, but while I'm here, okay, because this is the target, right? The end point. How would I swim? I obviously would try to swim 2 kilometers in the straight path, right? Right? Now, imagine, okay, let's say I managed to do that. An alien look at me, okay? Discovering the law of motion, that person would say the swimmer goes in a straight line. Does that make sense? Right? So the law of motion would be something like swimmer goes in a straight line from here to there. Okay? Now, what about principle thinking? What about principle? Well, the principle thinking is not to say, okay, this is how the guy swam. Why did he swim like this? Why did he choose this path? Because it minimized the effort. So it would be something like minimum time, minimum effort, right? And then based on that, derive the fact that the shortest path is a straight path. Does that make sense? Okay, does that make sense? Now, it turns out, okay, this is a big picture, right? This is 2 kilometers away. So I was aiming straight. I actually strapped Garmin to the back of my swim cap, because back then Garmin wasn't reading satellite signal underwater or with water. So I put it in the back of my head. I kind of adapted to run this. Okay, it turns out I wasn't swimming straight. Well, but that's not the point. The point is this. Watch this. I was aiming straight for the target, right? Now let's say the target is over here, and I'm over here. I'm swimming. Okay, so I'm really tired because I'm a slow swimmer. It's already like 3 hours and something. And this is the beach. Okay, this is the beach. Guess how I swam? Would I do this? Would I continue to go with straight line? Who thought I would keep doing what I did before, swimming in straight line? No, because swimming is a lot more tiresome than running. So what I did was basically I just swim like this and then I ran like that. Right? So think of what's behind it. The law of motion would not tell you, well, the law of motion would just tell you to go straight line, right? But if you think of principle, why does swimmer behave this way? Well, because he's tired. He wants to minimize the effort, minimize the time. Okay? It turns out this is exactly how nature operates. In fact, when you shine lights on the surface of when you look through the glass and you see the straw that it bends, why does light bend? Light bends precisely for this reason. Because light travels slower in a thick medium like water. So the ray that you see tracing is the one that minimizes the amount of time. Now, I was doing this in my head, so I wasn't sure which one is the quickest, right? It could be like this, or it could be like this, but certainly not a straight line, right? Well, the point is nature optimizes that, okay? So the second generation, so to speak, of physicists, instead of saying, hey, how does this thing move? They say, by which reasoning? Okay, as if we have a reason, okay? As if I have a reason. Well, I have a reason. As a swimmer, I have a reason to make a shortcut to the shore and then run the long way, right? Well, light does the same way. Okay, but light doesn't think, it just nature operates by principle. So that's kind of like a reformulation of Newton. That's going to give you a character called Hamiltonian mechanics. And that Hamiltonian is very important. Now, so doing physics is discovering law. Doing physics is discovering principle by which nature operates. Okay. Finally, I would say the modern generation of physicists. Doing physics means discovering structure. Okay, structures. It would be like, again, well, let's try that. Let's go back to original example. I had 2 examples already, right? Swimming, offshore swimming, and chess. So the first one would be, okay, this is how a horse moves. This is how a bishop moves, right? Right? And the second generation will be, what's the principle? The principle is the games just keep going until the king gets checked. Okay, so there's a purpose. There's a reason why people move. It's not random. Okay, there's a reason. There's an agency to it. Finally, discovering structure means like this. You look at people playing games. Yeah, you understand that the principle is to knock the other king out, right? But then you say you describe the whole terrain. What kind of structure gives this game? It's the game that allows for different kind of movement, right? Think of index in a chessboard as going to the right I, going up J, right? Then how would you describe a bishop? A bishop is something whose movement has I equal to J, right? Or maybe a negative sign of it, but same amount. So it goes diagonal, 45 degrees. How does Rook? Rook is the guy at the end. Does he move? He moved by making sure that either I or J is 0 because he only goes horizontal. Yeah, yeah. So the absolute value, like I said, it could be negative sign. The absolute value is the I and the J has to be of the same size. Otherwise, it wouldn't make 45 degrees. Okay? So that's how physicists would describe the structure. And this is how quantum mechanics was arrived at. Okay? Making sure that the physics has the structure that reflects reality. Now, the analogy that I like to use, which is why I put this thing here, I'm trying to, relate with your generation. I don't, but I'm trying the best I can. You guys play games, right? You guys play games. Certain games has certain rule of the games. So think of mathematics as a big department store of games. Okay? Some games has the rule that I and J has the same magnitude. Some rule has to have the game move where I has to be 0 or J has to be 0. And then you go look at people playing chess. Physicists go look at people playing chess, come back to the store and say, hey, what kind of game matches that? Well, sure enough, the games that match what you see in the park bench is chess, right? Now, of course, that's easy because the complete game is represented by a complete set of mathematics, like a whole set of games. But in physics, a lot of times you don't have a pre-made game. You observe nature, and it's a different kind of game, right? It's a funny kind of chess. So you can't really take the whole thing like wholesale. Say, oh, this is the game. This is how nature works. You have to build it up. Okay? And that's what quantum physicists at the early 20th century, what they did. They go to a mathematical store and say, what kind of rules do we need? Well, I need a rule called probability theory. I need a rule called spectral theory. I need a tensor product. I need to self-adjust. I need a whole bunch of stuff. So that once you put this and you play the game with all these components, it looks just like nature, except in the physicist case, it's not what you see on the park, but what you see by experimental physics. Does that make sense? Okay, so that's the science, right? The science. So all this is about matching nature, but it's matching nature or observation at different level. One is trying to say, hey, let's come up with some mathematics that describe exactly how nature moves. The other one is, hey, why would nature move this way? There has to be some kind of principle like minimizing cost or a shortest time or something like that, right? The other one would say, okay, forget all this. Let's just say nature. What mathematics does it take to describe nature? And if that set of mathematics isn't there, then you make it up by the existing component, right? So you go to the game store and you pick up this little part from this part allows you to move laterally. This part allows you to move diagonally. This part allows you to move really weird way like a horse, like a knight, right? And once you put that together, make it consistent, then it matches nature. That's how physics discover structure, by which I mean mathematical structure. Okay? Now, where do we come in? Well, I can say that this is Newtonian physics. Okay? Newtonian mechanics. Yeah? part of physics that has to do with motion. This one is called analytical mechanics. It has two names. One is Lagrange. So sometimes you will have a friend from physics department called Lagrangian mechanics. You have another friend called Hamilton. So Hamiltonian mechanics. Okay, but together they are called that pair is called analytical mechanics. Then this new way of doing things is called quantum mechanics. Okay, quantum mechanics. Okay, so that's the first insight I want you to get. Inside part of the lecture before we go to the mathematical tutorial part. Okay, does that make sense? Now, while I'm here, I'm going to add two more insights. Okay, I'm going to add two more insights. One is, once we get to quantum mechanics, how do we get to QC, right? Well, that's the same thing as once you have electronic circuit, how do you build a computer? That the first lecture we talked about, the adding 0 and 1, right? So you have to get some kind of very clever engineering. Okay? The engineering starts with the math. What kind of math can we do with quantum switches? Remember, with a regular computer, it was XOR gate and OR, right? So the engineering is what kind of math can you do with it? Well, no, we'll get to it. It's the whole course. So if you knew this, you don't have to take the course. Okay, what kind of math do you need? Okay, and it would turn out, like I said at the very beginning of the class, you should be glad. Because when I give you insights a little bit about how quantum mechanics works, you realize that the math is much simpler with quantum computing. So much simpler, okay? So insight number 2, you just take my word for it, okay? Take my word for it. The math, the structure, I was talking about structure earlier, the structure that describes quantum mechanics in general, it's a big game space. It's a big game space. It's like games in 3D dimension and all kind of moving parts, right? But then you make a dumb version of it or simplified version of it, like character can only move in 2D and you only have 2 colors and you can only shoot one type of rockets. You just make it very restricted, very simplified, and that's what you need for quantum computing. Okay, so you don't see it now, but just take my word for it. Insight number 2 is, yeah, quantum computing mathematically is much simplified vis-a-vis quantum mechanics in total. Okay? And then, of course, you do the math, and then you do the sort of like electronic stuff and all kind of things. So you have to do a whole bunch of stuff. Right. Oops. I don't care. Now, so finally, before we go to mathematical proper, I just want you to have the, well, it's not really insight, just kind of like separation of duties. Think of computer science as hardware engineering, hardware science, you know, people who do like very high-tech research at Intel and at TSMC, you know, how to make the nano chips so small without the interference, all kind of stuff. So this hardware science is very difficult, right? But then you got computer scientists who don't know anything about hardware. They just do the programming. They just do the coding, right? It's not much easier. It's still difficult, right? But it's in the realm of software. Okay? So the quantum computing, the insight, the last thing that I want to give you is this. As an emerging technology, there's a hardware side and there's a quote unquote software side. And hardware side, number one, not only am I not going to cover it, it would make little sense for Thai engineers to do that because we can't build hardware quantum reasonably well. It's a little bit like big data center. You need big money. Okay? So basically, this is big money. So let's leave it to the rich country. Let's leave it to the rich country. Okay? However, the software side, as you know, right? Same with the computing world. Okay, you can design a game and sell it to the global market and be just as successful as somebody in the United States or European Union. Okay, so the software side is where we focus. Okay. Software side, and that basically comes down to quantum computer programming. The difference is this. The difference is with classical computing, you don't go down to the zeros and one. Okay? The zeros and one turn into adding multiplication. Adding multiplication turns into variable, turns into function, and turns into command, turns into basic functional language, turns into Python, turns into C++. Then you learn over there. Right? Nobody nowadays program at the zeros and one anymore. Well, with quantum computing, this you would be programming at the zeros and one level. There's two reasons for it. Number one, okay? Number one, seems obvious. It's a new technology, right? So people who were doing classical computer, at some point they were doing zeros and one as well. But that's not the real reason. The real reason is that the classical computer, you can go from zeros and one all the way to C++ code and something as sophisticated as Mathematica because it does general purpose computation. Quantum computing, you don't build that stack from assembly code all the way to Python or whatever because it does not do general purpose computing. It actually does one thing: discover solution. It discovers solution not deterministically. You can still get it wrong, so that's even bad, right? It sounds like a bad news. In the regular computer, you can always get the right answer. In quantum computing, you can get wrong answer, but you have a high probability of the right answer. Why would you do this? Because that problem turns out to be so big that no matter how many computers, classical computers in the world you put together, it can't solve it. Okay, it's, you know, it would take the edge of the universe. Okay, so now let's go to the proper objective of this class, right? Everybody loads up the Mathematica. Yeah. Now, how many of you have done like Python? Yeah. You notice that Python and Mathematica, the startup screen looks similar, right? Okay. Because chances are, well, Python, you can write in any platform, but the most popular platform or the most popular workstation to work with Python is using Jupyter Notebook, right? And but to you, do you need to know VS Code? That's kind of back end, right? So as far as the appearance, what shows up, right, is Jupyter Notebook. Right. Okay, it's not a big point. Don't dwell on it. Don't dwell on it. It's not a big point. The point is that Jupyter Notebook was modeled after Wolfram Mathematica. That's the reason why you put Open Mathematica. It looks like Jupyter Notebook because the one who wrote Jupyter Notebook had the inspiration from Wolfram Mathematica in the 70s. Okay, so that's kind of like a comforting thing. But So what does that Jupyter Notebook interface mean? Okay. Well, a computer will do things that you tell it to using the program. Okay. You can write the whole instruction set wholesale, right? And then ask the computer to do it. Okay. This is a sort of compiler language. It's very efficient, it's fast, because the thing that you write in semi-English looking thing turns out into very low-level binary kind of thing very quickly. And that thing gets done really fast. So things like C, for example, in C++, it operates like that. It's called, well, it's compiler language. But there's more modern way of doing things like Python, where you don't necessarily give the whole thing. You can just give it one chunk at a time, and it would output, right? You can give it output from this chunk as an input to that chunk, and it will give an output. You can string all this together, and it would do the same thing. The point is that you don't have the whole novel. You just have one line at a time. You just feed this thing one line at a time, so to speak. And that, in a way, is called functional programming. In fact, that's not a definition of functional programming. You know, a computer scientist, it's not a big point. It's not a big point about functional. Yes, but interpreted language, yes. But more to that, I want to say functional program because the way you communicate with it is by calling a function. Okay, so think of it as a recipe. Think of it as a recipe. Okay, if I have a whole recipe for making banana cupcake and blah blah blah, that's the whole shot, right? Well, a functional programming is, again, it doesn't take compiler. That's a distinction between interpreted and compiler. But the distinction I'm after is the fact that it does things just one function at a time. It'd be like saying, okay, line number 1, crack an egg. Line number 2, take the result of that cracked egg, beat it. Now, line number 3, take the result of that beat egg, add some flour according to certain weight, blah, 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 blah. So every time you communicate with a computer, you ask it to do something. Okay, but you don't ask it in the same way that you ask ChatGPT. You ask it by calling a function. So if you wanted to beat an egg, you would say something like, okay, beat egg. You have to supply it with the egg, call the function beat, and then the result is called, you name it, y. Y is beat egg, right? And then you do something else like mix. Function, mix y with flour. Okay? And the result is z. And z becomes something that you bake or whatever. Okay? Now, this is what we mean by functional programming. Not only do you go line by line, even though you can send a whole bunch of lines together automatically, but it comes down to line by line instruction. But that line by line instruction is a function. So you don't say, please make me a coffee. You say, do you have a function called make coffee? Okay, I call that function. If the function doesn't exist, you make them. Yeah, it's called user-defined function. And how do you make them? Well, you make them from combination of built-in. So in every functional programming language, there will be a library of built-in function. And for your job, let's say you want to make a souffle, there's no function souffle, but that function souffle comprised of egg beating, frying, adding flour. You just put a bunch of built-in function and call it together, the whole string, the whole pipeline, your function. And that's called user-defined function. Okay? right? And so now, the only thing you need to do is that in functional programming, you work with variable, and then you work with function, okay? And then you get some kind of output, okay? And your logic is to string a whole bunch of this together, okay? In fact, you can write a whole program without defining your own function. But, you know, if you make souffle a lot of time, you might as well write like a souffle, egg, flour, and then you have a small step, beat egg, mix flour, this and that, blah, 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 blah. Right? So next time you just call it, do this. Okay? By the way, you can do that with large language model as well. In fact, I'll show you how. Okay, so that's it. So you have to understand that Mathematica fundamentally like, and this is all pretty much the only thing that you can say that Mathematica is exactly like Python. It is, in a way, mostly a functional programming language. Okay? Although, as you will see, it's more of a declarative language because it's a lot higher level. Higher level meaning it's more abstract. No. Okay, so let's try this. You guys start something, right? Start. Okay. What I'm gonna do is, okay, so that's it. I'm going to follow my textbook. Okay, I have a textbook in data analytics, and I'm kind of like drafting the textbook on quantum computing, but both will use the same mathematical tutorial section. Okay, now I gave you the copy of that already, but I don't recommend you start with. Okay, that's, you know, you read inside about, you know, where math. Okay, so basically this book. Okay. Chapter 1 on quantum computing is about, you know, introduction to quantum physics, just kind of like where it came from and so forth. Okay, so ignore that. That's a kind of insightful, blah, blah, blah. Okay, now introduction to Wolfram Mathematica. Okay, and here I don't need to show that. I can just do, okay. So the first thing first, how do you tell the Mathematica that, yeah, I'm done talking, it's your job? You shift enter, that's it. Okay, so let's do this. I'm going to do this really slow, and it's going to seem insultingly slow. Delete output. Where's delete output? Yeah. Right. At first, it's going to seem insultingly slow, but bear with me. Okay, so when you start, okay, you just type in something. Now, when you type in something, you don't type a text. By default, okay, now look at the screen. If you actually go to a new page, okay, new notebook, okay, when you type something, it's going to assume it's a command, okay? So when I say 1, where's 1? 1 plus 1, shift enter, that's a command, okay? Now, I just told you that you don't communicate to Mathematica. The way you communicate Mathematica is call a function. This doesn't look like a function. Well, in fact, it is a function. The function is called plus. Plus, now you use this square bracket. So let's do this again. Plus 1, comma 2. Okay. Get 3. Okay. Again, I'm going to go insultingly slow. Okay. But pay attention because it's one of those exponential. Okay. So I can put plus. It's the same thing. So in other words, the mathematical notation becomes like a shorthand for a functional programming. To you, this is the math. To the computer, that's what it does. It calls a function called plus, like mixing flour and egg, right? Now, this happens to be one of those functions where because 1 plus 2 is equal to 2 plus 1. So you get the same thing, right? Now, here's the thing. This function knows that sometimes you don't want to add just 2 things. So you want to add 3 things. So can you do that? Obviously, you can add as many things as you want. Okay? 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 And you get that. Fine. Not all functions are like that. Okay? This is very important, especially when it comes to user-defined function. Some function has only place for 2 things. Exactly 2 things, no more. Some function has 5 things, no more. And the first thing does this, the second thing does that, the third thing. So what do you think those are? Those are either variable or parameter, right? So let's go to last week. Last week we have a baby equation, right? Yes, remember the baby equation? Linear equation, right? Okay, so now that linear equation, okay, let's say Mathematica doesn't have it. It does, but let's say I don't have it. Okay? How would I do user defined? Well, I'm going to name this is because it's a user defined, I have to name it. Notice that when I type in the word plus, it's in black. Okay? Anything that's in black, it's known. This is kind of like a shorthand, a visual cue. If it's in black, it's built in. The thing knows. Okay? Number 1, it knows what it is. Okay? Now, let's say I type in the word A. Notice it's blue. Okay? Let's say shift enter. What's A? A is A. That's obvious, right? Because it doesn't know what A is. But the minute I say A is equal to 5, okay? Shift enter. Now you notice the letter A is black. So next time I use the word A, it returns 5. Okay? So the color will give you a clue. Okay. So I don't want to care about this, so I'm going to use another function called clear A. And A becomes blue again because I don't want to keep it defined. Okay. Now, let's go this my linear function. My linear function. Okay. Now, what's the linear function? Mx plus b, right? So I would define it this way. My linear function is a function of x. Okay. And this is a notation underscore to make it generic. So it's not just this x. Any x will do. And then m, comma b. I define it with equation, but, and this is the only thing you have to remember, use colon first, okay? M times x. Now, because multiplication is used all the time, all you do is just put the space, plus b, okay? Because you don't want a particular x. You say anything that goes in this place, you see. Yeah. So some of this is syntax, but there's a reason. What it means is this underscore is a sign that you are doing pattern matching. Okay? So anything that goes in this slot, I will match it with the pattern X, and I will use it in said way. So if I put 2, 3, 5, what's going to happen? It's going to think that X is 2, M is 3, B is 5. That's simple, right? Okay. So notice, and this is very important, I spend a lot of time talking to you about parameter versus variable, right? Right? In functional programming, you keep track of which is a parameter, which is a variable. Why? Why do I say that? Why do I say that? Because a parameter is a constant in a context, right? So in this context, I set m is equal to 5, but in other contexts, I can set m equal to 10. So why restrict function to m is equal to 5? Right? I could do that. I can do that. I can do that. But it would be very useless. Okay? Let's say instead of doing this, I say, okay, let's say my stupid function is a function of x is equal to 3 to 3x plus 5. The problem is if I did this, I have to do it for 3 and 5 and 7, so it's kind of silly, right? So even though m and b are parameter, I'll treat it as a variable. Again, if you've done some coding, this is going to be very painful and slow, but there's a reason why I'm doing this painful. Now notice it's blue now, right? So I shift enter. Are you typing the same thing? Just follow my thing. Yeah. Shift enter. I'm done talking. Please acknowledge, and my acknowledge is shift enter. Now my linear is a function. Okay. Now watch. My linear function x 3 and 5. Then it will give you exactly that. Right? Does that make sense? Okay. Now this is right away. By the way, in like a tutorial, there's a lot of things to go first before you get to this function. But I want to introduce this function very, very early on, and watch this. Okay. So now I know what this is, right? I'm going to introduce one function that you're going to use for the rest of your life. Manipulate. Is one word. Yeah. Okay. Yeah. So if you didn't put a space, it's not going to think m times x. It's going to think mx is a name. Okay. Okay. Now, well, let's before I do that, let's say, what does this look like? Plot. Okay. Plot is also a built-in function. My linear function x 3 5. Okay. Now I fix my m and b, right? Now notice, remember I told you that some function expect exactly the right number of argument. Argument is thing you put in the bracket. Okay. If I did this, watch what happened. There's an arrow that says, hey, I'm missing something. You're not finished. Okay. It's like a reminder. So it's kind of a nice reminder. Well, a reminder is you need something else. This function plot say, what are you plotting? I'm plotting linear function, x, 3x plus 5. But I have to tell it what value of x, comma, and then you use curly bracket, x from minus 3 to 5, to minus 4 to 20. Okay, just type this. Okay. Again, excruciatingly slow because this is you introducing a notation. Then I'm going to go really quickly. The minute you type in this plot, Mathematica expect at least 2 arguments. Okay, actually you can put more, but those are optional. The first thing is, what are you trying to plot? You're plotting a function of x. Well, if you want to plot function of x, you have to tell you what the range of x is, and you use the curly bracket to specify the range. Okay, shift enter. Okay. So there it is. Okay, there it is. Right? Simple as that. By the way, those of you who came from Python background would really appreciate this because matplotlib would take you only 5 lines to do that. More. Way more. If you do Python matplotlib, you do a lot more just for that. But anyway, well, what the philosophy of Mathematica is this. Make a function simple. If it's not to your liking, enter the option. So it's going to assume this is what I want, right? But I don't have to set up everything. So whereas my plot lib, you have to set the frame, you have to set this, set that. This thing is just going to automatically assume it knows you. But if you don't like it, you can tell it so. So one of that is to add the third option. Okay, third option. Let's say I want this image size to be small. Now, this is another notation because it is the name of an option. It's a image size is, and it's going to suggest, and of course you can say something like small. Okay, or you can keep it in some kind of a numerical pixel size or something like 50 or something. Where's my pointer? Where's my pointer? Yep, there it. Where did it go? I don't know where my mouse. Sorry, because you got some kind of syntax error. Okay, if you type exactly like I tell you, it's gonna work. So tiny. Right. Well, you get the point, right? So instead of having to set up, define every single thing about your graphic, like in my plotlib, it's just going to assume what seems like a reasonable case. And you can actually set global default. Okay. Anyway, so this is not so much fun. Now, this is the key. Hold on, don't go anywhere yet. Don't go anywhere yet. Okay. What did I say about 3 and 5? They are parameters, right? It's a constant now, but I can change it later. So why don't we do exactly that? Okay, why don't we do exactly that? But I'm going to do it in a clever way called interactive visualization. So instead of doing this, okay, let's go back to the, why can't my mouse be where I want it to? Okay, so what I'm going to do is, yeah, you got this, right? Got this, right? Now copy this and paste it below. Same thing. Okay. What I'm going to do is this. I'm going to make this thing okay, manipulate. Okay. I'm going to embed it in this. Okay, just to be sure, I can shift so that you would see that it's on a separate line, but it doesn't mean anything, right? So, okay, same thing. Okay, what I'm going to do is this. I'm going to make one of these parameter called m. Okay, m for slope. Okay, and I'm going to make comma behind this, and I say my m goes from say -1 to -10 to 10. Okay. Now, notice I'm going to write this in a separate line so you can see. This function plot has two arguments. Argument meaning things I put in the bracket. Okay, now you guys see that? Oops. Okay. The function plot expect at least two things. What are you plotting? Over what range? So I gave it two things. Manipulate also expect at least two things. What are you going to manipulate? And the range of manipulation. So it looks almost the same, except it works a different way. It works like this. The x from -4 to 20, that's the line. But the m becomes your parameter to control. So this becomes, see that? So now I can control my m. Yes. Yes. Right? from negative to positive, right? Well, I don't want to just control my M. I can also control my B. So there it is. Make it B. Okay. B from, say, minus 10 to 10 as well. So that's not going to be that exciting. It's just going to shift up and down. Okay. Whereas this thing is going to change the slope. Okay. Does that make sense? Okay. So this is really boring, but this is the key thing that we're going to use the rest of the semester. Okay. You tell it to do something. If that thing is built in, okay, and Mathematica has like 9,000 of them. Okay. So you're going to do a lot of heavy duty mathematics. It's already built in. But if you want to piece the mathematics together, do this to x and do this to y and do this to x and y and then add z and then do this to w and blah, blah, blah. That's your own recipe. You have to build it up by defining the function. How do you define a function? With colon equal, right? And you go, once you define it, you use it in the same way as a built-in function. The special function that I want you to know is a function that has to do with plotting so that you can visualize stuff. The other thing is manipulate. So these are the two things that I use almost on a daily basis. Okay, for everything. Everything. I want to see what this function does. I plot it. But I don't want to plot it for just a particular value of parameter. So I set the parameter into a range that I can play with. Okay. So once you got this concept, okay. Yeah. Now we're going to go fairly quickly. Right. Does that make sense? Now, who wanted to go to? Okay. You can go now. You can wait. Okay. I'm going to start with this. So, oh, one more thing. One more thing. Semicolon is a way of saying, don't show me the result. So what do you think happened when I do this? And this is just the last structural thing I need to point out. Two lines mean two commands. Okay? If I want to put more than one command in one line, I have to put semicolon. What's bad about it is that because in that line, it's going to give you an output. If you put two commands in one line, the first one is separated by semicolon. It's not going to appear. So that command is to say echo number one, echo number two. Go ahead and echo. Okay? So what's going to happen here? I'll get up quantum operator. Not so quick, not so quick, sorry. Again, I want to go excruciatingly slow. And then go. Page down, page down. Then up, chapter 1. Okay. Read this, by the way. This is underlying physics. What is quantum physics? Having problem with this. Yeah. I don't know why. I don't know why my mouse, when I put it over here, it's too big or too small. Okay. Okay. Now I hide chapter 1. I can hide this. Evolution of Mathematica. I don't need that. Mathematica notebook. Okay. Now. Okay. See? Again, very simple, but remember, I put in the function for 1, it's going to give output for 1. But because I put two functions, one for 1, one for 2, and I put semicolon, it's just going to suppress this, right? And give you 2. In the next line, 3.4 equal to 7. Does it give you 7? No, it doesn't suppress it. Okay. Just so you know. Just so you know. Okay? And now, sometimes blue, you can do this as well. Because again, whereas with matplotlib, you have to specify that this is a function. Does somebody have like a string mouse that I can use? Never mind. Okay. So blue, shift enter, I just get blue. Actually, this is a function. This is called RGB function. Now, let's go to the fun stuff. Fun stuff is, let me clear all cells, delete all output. Yeah. Now, this is what's cool about it. It's such a high level language. I told you that it has, who here has chemical background? No? Okay. Well, let's say I want to know what caffeine looks like because I drink a lot of caffeine. Okay? All I do is this. Shift enter. Shift enter. Okay? Now, the first time, it's going to take a while. This is one of those. Initializing chemical database because I don't have chemical database globally. So the first time I call chemical database, but this is going to take a long time. But see how simple it is? This is actually a caffeine database. Well, not caffeine, molecular database. Okay? So it shows you what caffeine look like. This is, I think this is, yeah. Built it. It has its own library. It's, yeah. Wolfram is like a universe in its own. People just add to it. Okay. No. 20 years ago, probably didn't have this because chemists didn't use Mathematica. Mathematica was created for physicists first, then mathematicians, and now everybody, artists, whatever. So there's like art library, there's AI library, there's chemistry library, there's linguistic library. So this came much later. Okay. But now that in 2026, a lot of chemists work with this. So now you can do this. And in fact, you can do all kind of different kind of plots. I'm not going to show you because I'm really frustrated with this mouse. Anyway. Cursive table. Oh, sorry. This is just me being, aesthetically demanding. Palette, special character. Now, I just happen to write a lot of things myself, and I like the code that I write to have a special character. So I use this kind of funny table. This okay. Don't follow my example. It's aesthetic. Basically, it's like font. Okay, it's like font. Just use standard font, guys. Don't be fussy. I'm just a little bit annoying sometimes. I like to make things look pretty when I don't need to. I created this table function. It's you don't have this because it's one of those user defined. Okay. You have to define it. I defined it in that file. Okay, I did it. Yeah, before file. That's why, and I use it a lot. So I have, but you don't have to do this. By the way, you can use a built-in version. There's a built-in version of the function I got. Why this? Can I? Hopefully light is better. Actually, I found out that sometimes it's not the mouse, it's the surface. Yeah, this is better. So Where were we? Okay, we were saying that this table, okay, don't use this table function. I think it's yeah. So instead of using this thing, just use grid. Yeah, grid. Yeah. There. Now grid is a built-in function. Um, it expects a few things. So actually it needs one more bracket. I'll tell you. I won't explain to you why, but yeah, there. So it looks almost like what I got, except it's not as pretty. The reason is it doesn't have this frame. So how do I add this frame? How do I add this frame? Put in a comma, frame, all. Add all. Okay? So something like that. Okay? Now I put the bracket, too many brackets, so it kind of, this thing is supposed to go in a different one, but I put in a different bracket, so hold on. Correct that bracket. It's not the mouse, right? It's something with the, yeah? There it is. I don't know why it's so slow. So I'll remove one of the bracket here. And there it is. I put it right. Okay. Yeah. So that's not, let's not dwell on this. But let's go down to mathematical. So some of this we can play on your own, blah blah blah. Again. Now, no, you just go to Wolfram reference page. Okay. Now there's something else that again is a newer version. You guys think you guys know how Wikipedia works, right? It's like a storehouse of information. Yeah. Now imagine I want to do calculation on information from Wikipedia. What would I have to do? I have to go to Wikipedia page. Let's say I want to calculate solar mass as a ratio of Earth. I have to go to Wikipedia page on the sun, Wikipedia page on the Earth, and then take the two number and divide, right? Well, think of Wolfram Alpha, it's another universe, as a Wikipedia that you can calculate on. So you would look up the word sun. But once you get the word sun, it becomes a number that you can calculate. Yeah, so this is just something that I'm not going to go over it today because it's very useful for data analytics class uh, that I used to teach. Yeah. So for example, where's the sun example? Like this, for example. So the idea is instead of looking up solar eclipse, you just type in solar eclipse in Mathematica. Okay. And then shift enter. And it's going to retrieve all kind of information as if it's a Wikipedia page. Okay. Again, the first, it's got all this solar, lunar mass, and all that. But once you get this, you can compute on it. Okay. I think something that is just a feature I just want to mention. Okay. Now let's go. I'll skip a lot. So see, it has a lot of stuff. Central duration 7 minutes. Maximum eclipse. Okay. When you go to new page, sorry. Okay. You will notice I want to type something in here, right? Once I put the mouse in here, if I can put the mouse in here, you see there's a plus thing here? See there's a plus thing here? That plus is a prompt for you to specify the mode. If you don't specify the mode, it's going to assume the formula. Because most of the time, functional programming works with formula. But if you want to type in something else, and these are the options, okay? These are the options. See? This is the default option called Wolfram language input. Next, plain text. Plain text means text. That's what I use to write the textbook. Other style of text, well, this is kind of like heading, subtitle, stuff like that. Basically formatted, pre-formatted. Chat input, you can use this for basically it's a large language model built inside here, but never mind. Chat break. These are kind of like new feature I never use because I already have ChatGPT. Okay. Now, this line is called freeform input. This is when you can't think of anything, you just type in and see if it's going to come up with a autofill function. The one that I was telling you about earlier is called alpha query, right? So this is Wolfram alpha. So this would be like finding about something. Now, notice the right-hand side, there's a shortcut. So let's do that. Let's do the shortcut. So instead of doing this, I just go equal, right? Say, what do you want to know? New, okay, Einstein. Yeah, shift enter. Now this is going to search just like, you know, what, unfortunately, this is a biography, so it's not going to have a lot of computation. But let's say, yeah, it normally is quicker, but this thing is so slow. So this is like a Wikipedia on Einstein. Unfortunately, you can't do much calculation, but you can do something like, what did I do before? Sun, right? Or something like, let's see, Planck, constant, shift enter. It's going to come out. So it's going to have a whole bunch of stuff. Okay. Now, some of these are useful if you're going to do data analytics because instead of having to go always to like a data search, you can just basically prompt it. And these are very easy way of doing it, but it's not the emphasis of this class, so I'm going to skip. Okay. Yeah, so it has a built-in LLM. I don't think it's in the student licenses. So anytime in my notebook, you see this reference, you can just click it, right? Tools for AI, control state. How many of you are from engineering school? Okay. Do you know what optimization is? Well, in optimization, if you use MATLAB, you could do optimization, but it takes a lot of code as well. Here, you just go to optimization, and you will see that it has word like find minimum, find maximum. Oops. So sometimes you don't even have to say what mathematical programming algorithm does. It's going to say, okay, find minimum, find maximum, all kind of stuff. Okay. So this is something good used for engineer. Okay. You recognize this, right? This is like a second year engineering, except so minimize function f of x, okay, subject to constraint. So this would be like you want to minimize travel time for logistics. You want to maximize profit given that you have a current stock. All kind of linear program methods. Anyway, so this is a side note, guys. It's again general ed. I can say anything, but this is not immediately relevant to quantum computing, so I'm not going to spend so much time on it. And another thing that requires you to load, this would be something like example data, statistic. I can do that. So I can do that. Again, this is from my data analytics class. Now, one thing I want to show before we move on to a break is that manipulate that you did that I show you, right? Instead of using it as interactive visualization for yourself, you can think of it as an app prototype, right? Except that app prototype has to do something more than plotting a line. So plotting a line that forever. Let's say, so I make something funny. I hope it's funny, but it's not that funny. So let's say something like this one. Yeah. Shift enter. So basically, it's randomized lucky number. Okay, let's say you just want to create an app. So my lucky number is red, but what kind of red? Let's make kind of red, blah blah blah. So let's say this is an app. It's something that you make for your friends or something like that. Okay, right? So notice it doesn't have to be a mathematical function. It can be any kind of geometric shape, picture, all kinds of stuff. The point is you have a button to control it, you have a slider to control it, you have a way of controlling it, and more importantly, I hope this doesn't take a long time. You can say, I cloud deploy it. So once I cloud deploy it, I'm not going to do it now. You're going to get a URL. Literally, taking this URL, get an password. So instead of prototyping your software, you have to sort of like bring the software. You can literally deploy file, and then if you want to pitch it or something like that, you just give this address. Okay. So for project on cloud, that means we don't have to write it. No. The computer runs first, and then it kind of encapsulates this object and put it on cloud. What about the big project? Not a big project, not a big project. For one thing, it's much slower to run on that path. Okay. I have a software that has to do with attribute optimization, and I apply for patent. But in order to demonstrate the concept, I write a little software that is that, and then I can capture the screen and print it, or if the problem is small, unfortunately this one's not small, I can cloud deploy and demonstrate. Okay. But this cloud deploy is kind of like a fun thing. I don't use it that much because folks. Exactly. I mean, for example, I can say, for the homework, build interactive visualization of a student. Okay, let me say the homework. When you that student, 3 lectures down, and say, okay, I want you to visualize, show me interactive visualization of a quantum field student. Once you did this, you can send me the mathematical code, I can spell it right, or you can cloud deploy it, send me the, right? And then this is how I create the homework. I click, I'll go to your name, I'll click, didn't work. Hey, simple as that. But that's a bit off because before we still haven't learned any quantum bit yet. Now, the cool thing, and this is, let's take 5 minutes break. Because when we come, things gonna go fairly quickly because I want to show you the sophistication. After the break, now prior to this, I said if you do math calculation, it's gonna take you 10 lines to do what you did last year, but it's still doable. After the break, I'll show you something where it's not doing right at all, no matter how many lines, except very rare specialist library. Okay, back in 5 minutes. Oh, no problem. Hold on, let me kind of there's a stop recording.